Hey everyone. So today we're going to break down something that's absolutely fundamental to understanding data, descriptive statistics. Now that might sound a little academic, but trust me, it's really all about a simple idea. How do you take a mountain of messy, raw numbers and distill it into a story that actually makes sense? You know that feeling, right? Someone hands you a spreadsheet, and it's just this overwhelming wall of numbers. It looks like total chaos. So the big question is, how do you cut through all that noise? How do you find the pattern, the insight, the actual story that's hiding in there? Well, the answer is actually pretty elegant. It really just comes down to four core concepts. In statistics, they're called the moments. You can think of them as four different lenses you can use to look at your data. Each one reveals a totally different and totally critical part of its character. Okay, let's start with the first moment, the center. Before we can do anything else, we have to find a single number that represents the typical value in our data. Where does all the data seem to cluster around? The most common way to do this is with the mean, which I'm sure you know as the average. You just add up all the values and divide by how many you have. The best way to think about it is as the balance point of your data, like the exact spot on a seesaw where everything would balance out perfectly. But the mean isn't our only option. Next up, we have the median. The idea here is maybe even simpler. It's the exact middle value after you've sorted all your data from smallest to largest. And finding it is really straightforward. First, you just line up all your numbers in order. If you have an odd number of data points, the one smack dab in the middle is your median. If you have an even number, you just grab the two middle values and find their average. It's as simple as that. So why do we need both? Well, this example with US family income makes it crystal clear. The median income is about $43,000, but the mean is way up at almost $61,000. That huge gap is because a few people with incredibly high incomes, we're talking billionaires, are pulling that average way up. The median, on the other hand, isn't affected by those extreme outliers. It stays right in the middle, giving us a much more accurate picture of what a typical family actually earns. This is why we say the median is a more robust measure. And finally, our third measure of center is the mode. This one's the easiest of all. It's just the value that shows up most often in your dataset. If the number 2 appears more times than any other number, then 2 is your mode. Okay, so we've found the center. But that's only half the story. The second moment is all about the spread. It answers the question, how tightly packed are the data points around that center, or are they scattered all over the place? And this is why spread is so incredibly crucial. I mean, imagine you have two datasets. They both have the exact same mean, let's say it's 50. But in one of them, all the numbers are crammed between 49 and 51. In the other, they range from 0 all the way to 100. Are they telling the same story? Absolutely not. To capture that difference, we have to measure the spread. The key metric we use for this is variance. The concept is pretty simple. For every single data point, you measure its distance from the mean. Then you square that distance, which just makes everything positive, and then you take the average of all those squared distances. A bigger variance means the data is more spread out. Now, here's a little detail that trips a lot of people up, so let's clear it up right now. If you have data for the entire population, like every single person, you divide by n, the total number. But in the real world, you almost always have a smaller sample. And when you use a sample to try and estimate the whole population's variance, you need to divide by n minus 1, your sample size minus 1. It's this tiny little tweak that corrects for the fact that samples tend to underestimate the true spread, and it gives you a much more accurate result. So variance is powerful, but it's got a weird quirk. Its units are squared. So if you're talking about money, your variance is in dollars squared, which is just bizarre. That's why we usually take the square root of the variance to get the standard deviation. This brings the measurement back into the same units as our original data, back to just dollars, which makes it way more intuitive to understand. All right, now we get to the really interesting stuff. We've found the center and we've measured the spread. Now it's time for the third and fourth moments, which describe the actual shape of our data. Is it symmetrical? Is it lopsided? Does it tend to produce a lot of crazy outliers? The third moment is called skewness, and it does exactly what it sounds like. It measures the asymmetry or lopsidedness of the data. A perfect symmetrical bell curve has zero skew, but most data in the real world isn't so perfect. Skewness tells us which direction the data is being pulled. And it's actually pretty easy to read. If the skewness score is positive, it means the distribution has a long tail stretching out to the right, toward the higher numbers. We call that skewed right. If the score is negative, that long tail is stretching to the left, toward the lower numbers, and we call that skewed left. Simple. Okay, now for the fourth moment, kurtosis. And right off the bat, I want to bust a very common myth. A lot of people are taught that kurtosis measures the peakedness of a distribution. That is not correct. As the statistician Peter Westphal put it so clearly, kurtosis is related to the tails of the distribution, not its peak. So, if it's not about the peak, what is it measuring? It's measuring tailedness. Basically, high kurtosis means your data has heavy tails. This means the distribution is more likely to produce extreme outliers than a normal distribution would. It's a direct measure of how prone your data is to those really wild, far-out values. We even have some fancy names for this. Distributions with high positive excess kurtosis are called leptokurtic. Just remember, that means fat tails, which translates to more outliers. On the other hand, distributions with negative excess kurtosis are platykurtic. That means thin tails and fewer extreme outliers than you might normally expect. So let's bring this all home. We've looked at the center, the spread, and the shape of data. These 4 moments aren't just abstract numbers for a textbook. They are the absolute key to unlocking real-world insights. When you put all 4 of these measures together, mean, variance, skewness, and kurtosis, you create what you can think of as a unique statistical fingerprint. This fingerprint can describe the fundamental character of almost any data set you'll ever come across, and it does so in a really concise and powerful way. And believe me, this is not just academic theory. These 4 numbers are the engine running behind so many critical real-world decisions. Insurance companies use them to assess risk. Doctors use them to understand the accuracy of medical tests. They're fundamental to weather forecasting, stock market predictions, and even the spam filter that's working in your email inbox right now. Look, understanding these 4 moments gives you a brand new lens to see the world of data. It helps you transform that noise into a real narrative. So the next time you're faced with a data set, you can ask the right questions. You know the 4 numbers to look for, and you can ask, what story is this data trying to tell me?